Hello everyone. A very good morning, afternoon, or evening, depending on which part of the world you are in. I'm Bhupesh Sharma, and I'll be taking you through this talk, which focuses mainly on optimizing SoC boot flow, primarily using open source firmware. We'll discuss some approaches, the current status, and the challenges ahead of us. So let's begin. Before we proceed further, I would like to acknowledge the Balai people, Gurang people, Gurang people, and Taribalang Bunda people upon whose traditional land we are gathering today. We pay our respects to the elders, past and present, and extend their acknowledgement to all the First Nation people here today. Okay, so first a few words about myself. I'm Bhupesh Sharma. I presently work with ARM as a team lead. I have been working on bootloaders and kernels since the last 18 odd years, and I have experience working with and contributing to several open source projects ranging from bootloaders to Linux to user space. I have also donned co-maintainer hats for several kernel and U-boot drivers. Currently, my interest area is standardizing a zero-day silicon bring-up so for newly taped out SoCs, which implies that having the software and firmware fully ready to be tried onto the silicon as soon as it is taped out from the fab. Okay, so let's start with the outline. Today, what we are going to discuss, we are going to discuss the what of firmware, how the open source firmware benefits us, and also how we can optimize the boot flow on SoCs. I'll share an example of the design approach that I used for the Qualcomm IoT SoC boot flow last year. And towards the end, we will also discuss some challenges facing us today and also ponder about the next steps that we can take together. Note that in this talk, I'll be mainly discussing firmware types that run on the ARM core based SoCs. So let's move to the first topic. What is firmware? Right. So what is firmware? As you know that you can find several similar sounding definitions about firmware, but primarily we can all agree that the low level software that is embedded into the hardware is firmware, and it is required to put the device into a sane usable default state so that it can perform its basic functions. For example, we have a camera on the right hand side, which requires the firmware to set up the image processing pipeline, storage interface where the image would be stored, and setting up the lens assembly so that it can be in its correct default state. Note that an important property associated with firmware design is that it should be updatable atomically. So more on that in the upcoming slides. Right. Note that depending on the underlying device and its end use case, there can be various type of firmwares present and co-working on the same device at the same time. Consider an example of two different firmware types, namely the Wi-Fi adapter firmware and the power management IC firmware co-running on a mobile device, for example. There can also be several other kind of firmwares running on the mobile device at any given point of time. For example, one required to set up the auto DSP, and they all might be required to run serially in a parallel fashion or a mix of both. Now, let's broaden the canvas and consider the scenario where we have a system on chip, aka SoC. So let's consider as an typical ARM-based Qualcomm SoC, which can be STM845, let's say, which can be running or STM845 based mobile phone. It has several blocks, as we can see in the picture on the right hand side, which can be related to the overall security of the device, its power management interface, that is battery life. Dedicated block on the SoC might also be present to improve the boot flow speed. Also, there can be several peripherals, audio DSPs, PCI interfaces, Wi-Fi, etc. Most of these would require some kind of firmware to run with, right? So we will have several firmware types stored and running on the SoC at any given time. Now, we go a step further. Considering a complex ARM-based SoC, say the ARM Neoverse based automotive SoC, we can broadly divide the SoC into compute subsystem and the peripheral subsystem. Here, we can see the compute subsystem on the left, which usually comprises of a Cortex A application core or cores, and the Cortex M core or cores, which are usually DSPs or coprocessors. So while the bulk of the compute work is done by the application processor, the coprocessors such as the SCP and MCP in this diagram are responsible for power management and baseboard management control functionality, respectively. On the right hand side, we can see a typical I/O peripheral subsystem which contains I/O peripherals such as the hard disk, display, Wi-Fi, USB, etc. Note that we would have specialized firmware running on each of the block elements. Refer to the ARM confidential compute ARC specification for more details. I have shared a link for the same in the slide. So let's now look at each of these subsystems closely, starting with the compute subsystem. The compute subsystem firmware basically decides the overall boot flow used by the SoC, and thus the design choices here actually affect the overall SoC boot to kernel prompt time as well. So let's try and understand which firmware variants come into the picture when we power on or cold boot the SoC. So as we can see on the right hand side, the Cortex M based coprocessors, namely the SCP and the MCP firmware runs first, where the SCP is responsible for the power management interface and the MCP is responsible for baseboard management control functionality, which is used on the ARM based servers. The BMC interface is primarily used for remote monitoring and management of the system. On the left-hand side, we can see the typical Cortex-A compute application core. And note that the application core and the coprocessor communicate through some kind of mailboxes, which can be implemented through a messaging handling unit IP provided by ARM, which is also called MHU. Note that this is still a fairly simple boot architecture because as we add new firmware components which deal with the root of trust, security, partitioning between the secure world and the non-secure world execution environment, things start to become somewhat complex. So, as we can easily infer, as one adds more and more features, the complexity of the boot flow also increases, and the firmware involved also increase proportionally. So let's talk a bit about these features. Let's say we add features like root of trust, power management, bootloader, operating system loaders, or it can be even RTOS loaders to the boot design. As you can see now that the boot flow starts to become a bit more complex. We introduce a new Cortex M-based coprocessor here, which is called the Runtime Security Subsystem, aka the RSS, which provides the root of the trust chain. It is the first booting element in the system now when it's powered up. The SCP and the AP flow remains pretty similar. So to what we discussed in the previous slide, notice however that the ARM trusted firmware, which provides a secure monitoring service to switch between the secure and the non-secure world execution environments, is now differentiated depending on in which execution environment it is running in. Also note that since this particular example is for an automotive reference design, MCP, which is primarily for ARM-based server designs, is not present here. So, as we can infer, we will need to consider these aspects for designing a set of robust firmware. Number one, hardware considerations. So, these will include your available RAM size, available flash or non-volatile storage space, underlying CPU type, and the data in the instruction cache sizes that are available with the CPU, available set of peripherals, and how they are connected to the system memory. Number two would be the software considerations. So these might include, for example, the choice of software to be run. These can either be, for example, a bare metal code or a rich operating system or even a real-time operating system. Also, how big and frequent are your firmware updates? That's an important software consideration. Also, the firmware footprint, what's the storage requirement? And the third category would be the ease of use. So these might include, for example, things like your battery life, security, encryption, and connectivity options, for example, Wi-Fi or Bluetooth. Now, so let's quickly recap what we have discussed so far about the device firmware. firmware is required to set up the device into a known default sane state. We also discussed that why our system firmware should be designed carefully so that the features that we need to support and the end use case that we need to cater to are actually fulfilled. And we can actually look for already available open source options as well, which preferably are compliant to some kind of specifications which are widely accepted, that will actually help us not reinvent the wheel. So let's go through some of the open source firmware related aspects. The first question that comes to mind is, why open source firmware? The first reason, I guess, would be that we don't want to reinvent things, right? So ARM already provides a good ecosystem when it comes to designing and testing several firmware variants. So let's take an example also for the DAS U-Boot open source bootloader. It has very well defined release version management, and one can gain a lot by getting changes reviewed by the maintainers. So another aspect is that boot firmwares like, for example, UFI, they adhere to written specifications and their open source implementations. For example, the EDK2 Tiana core can be run with other firmware or software stacks for quick interop checks. So these are the advantages that open source firmware really provides us. Okay, so let's go through the open source firmware approaches that we can take for the compute subsystem. Remember that we had discussed earlier that the compute subsystem mainly consists of the application processor and some dedicated co-processors like the SCP or MCP. So on the right hand side, we can see the set of features that we have already talked about in the previous slides that a compute subsystem would normally support. So what are the approaches available? The open source firmware approaches that are available for the compute system include using ARM trusted firmware to provide secure monitor services, using bootloaders like DAS U-Boot, which run in the non-secure world to provide EFI services, which using which we can, for example, boot GRUB2 or operating system subsequently. Instead of the DAS U-Boot and the EFI approach, we can also directly use the EDK2 Tiana core EFI boot firmware directly to boot the GRUB2 and the operating system subsequently. Also note that the hardware or the power state description here is usually supplied by the device tree blobs or the ACPI tables respectively. And now the open source firmware approaches that we can take for the peripheral IO subsystem. The first would be to use, for example, LVFS to get the latest and the greatest firmware updates from the hardware vendor directly. Usually these are signed updates, so we can actually check the signature of the firmware to ensure that the signature verification is also met. Also, we can use the open source Linux firmware package, which contains firmware as binary blobs, which can be used to set up your hardware peripherals into a sane runnable state. So these are the open source approaches available to us for the peripheral subsystem. Now, I will share the open source firmware implementations that are already available for the ARM world, the ARM ecosystem. So here you are. As you can see, we already have open source projects that provide secure monitor services, bootloader functionality, and BMC reference implementations. So feel free to evaluate these for your next ARM project. Also, note that these days, both while booting the vanilla Linux kernel or Android on an ARM-based device, the time taken to reach the Linux prompt or the Android user space has become really a critical key performance indicator, KPI. This is especially useful for IoT or handheld devices, for example, a smart thermistor. Normally, the compute subsystem has multiple cores and the boot firmware just runs on the primary core, with the secondary cores just sitting idle. Over the past few years, there have been several design approaches that have been discussed and implemented in the ARM ecosystem to optimize the overall boot timings. So, handing over some of the dedicated features, for example, power management or security management, to a dedicated coprocessor seems to give us shorter boot times. So please feel free to evaluate these approaches as well for your next ARM project. As we discussed earlier, and an example is shown in the slide, the approach that we discussed where we pass some dedicated management work to a coprocessor. For example, the RSS here provides the SoC's root of trust. We have already discussed what a RSS is in the previous slides. Also, the SCP, which we have also discussed in the previous slides, handles and provides the power management interfaces. So last year, I worked on and proposed an approach for optimizing boot flow on Qualcomm IoT SoCs. These IoT SoCs were using the same boot flow as Qualcomm mobile SoCs, thus using the redundant Android bootloader along with few other redundant layers of boot firmware. As we can understand from an example of a smart IoT thermistor, we might not need to run full Android on that IoT device. So I replaced these layers with a leaner thus you put implementation on the Qualcomm Robotics RBX family of boards. Here you can see the unified boot flow working on the Qualcomm RB1 and RB2 boards. The approach uses the same boot firmware and the upstream kernel on the two boards, with the only difference being the device tree blocks. I have already upstreamed most of the initial support code for the same. Right. So you can see the RBX unified boot flow strategy presented by Qualcomm in the referred keynote, describing the changes basically that I proposed in the boot flow. Using the new boot flow, we were able to gain several seconds, if I remember correctly, of improvement in the boot to kernel prompt KPI in the initial runs. Right. So let's quickly recap what we discussed so far about optimizing boot flow. So one can make booting faster by removing redundant and possibly proprietary firmware layers and replacing them with leaner open source equivalents. Also, depending on the end use case, we can utilize the compute power of the secondary application cores to achieve parallelization or a mix of serialization and parallelization, depending on the underlying use case. Now we come to the challenges in front of us. I think the primary challenge in front of us for choosing the right firmware design and getting faster boot times with the boot firmware is actually standardization. So I will not discuss the various flavors of the ARM boot requirement specifications here in interest of time, but you can go through them on the ARM documentation website. After seeing the boot requirement specifications and understanding the end use case of the new device you are going to design, you can actually notice that one size really doesn't fit all. So hardware resources which are available to us, for example, the RAM or the non-volatile storage space, and the software choices that we make, whether we are going to boot a bare metal software or a rich OS or a RTOS, they actually eventually decide the overall device firmware design. Another big challenge is to maintain an open source first approach. Okay, so what can be the next steps that we can take together? So first can be in absence of a real hardware or when the hardware is still under design, I would suggest that we use virtual platforms like Quemo or ARMFast models which are already available to evaluate your firmware and software stacks early. This will ensure that you are ready with your firmware and software design when the real hardware arrives is available. Also, you can use low-cost reference platforms like the Raspberry Pi to evaluate similar firmware flow decisions that you are going to use on the real SoC before the real SoC is actually available. Also, although it might take some time initially, but I advocate a open source first policy. This allows for better code reviews and fruitful interaction with the overall development community. Okay, so thanks a lot for listening to me so far. As always, these slides can be found on my GitHub page, and there are some reference materials available in the next slide. In case of any questions, please feel free to ping me on my X or Twitter handle, and I would be happy to answer them. Thanks a lot.